This next example comes out of section 7.3, solving exponential equations. This is one of these real-life type questions that actually relates to real life, unlike some of the ones in the book that we run into. Investing money and investing it at various interest rates and various types of accounts. This particular question, we have $6,000 investment put into an account that earns 5.64% annual interest, and the question is how much money will be there after 10 years if the interest is compounded annually. You hopefully have run into an equation that looks like this in your math past, that says A equals P times 1 plus I to the n. Now A is your final amount, what we're expecting to end up with here, which is what we're trying to find in this question. P is your principal, your starting amount, which in this case is the $6,000. I is your interest per compounding period, how much interest you're getting each time they compound it. That's important that you write it that way and not just annual interest, because n is the number of compounding periods. Now, it's not always the number of compounding periods. In this particular question, we have the simplest possible way, which is A equals 6,000 is our principal, 1 plus 0.0564, because you have to change a percentage into a decimal here, to the exponent 10. And so it just now becomes putting those numbers into your calculator to figure out what that amount is. Makes sense to round this to 2 decimal places, since it is money, and we have $10,385 and about 69 cents in the account at the end of 10 years if it was compounded annually. Now, part B of this question says, well, what if they said compounded monthly? What would we do differently? A lot of the question will be the same, in that I would still start with the same equation, A equals P times 1 plus I to the n, but although my principal is the same, the bank is not going to give me 5.64% every month. It's giving me that as an annual interest rate. So I take my 0.0564 and say, well, 1/12 of that is what I get every month. And if you do 0.0564 divided by 12, you're getting less than 0.5% per month. That sounds like a bad idea, but instead of 10 compounding periods, we have 10 times 12 months, which means 120 months. So I've got 6,000 times 1.0047 to the power of 120, exponent 120. And so if you do that on your calculator, you do get a slightly larger answer than we had in the first part. Still in the same ballpark, but $10,532.21. So it's a bit better deal for you to get your interest compounded monthly than annually if everything else is equal. Same principal, same annual interest rate, etc. So just to drive home the point, try this one. What if it was compounded daily? So if you're watching this as a video, pause it and try to do it. See if you can do it on your own. Start with the same equation, and I'll solve it obviously here down below. So 6,000, 1 plus 0.0564. We'll ignore leap years and just say there's 365 days in a year. The difference between that and truly a leap year wouldn't really be that big of a difference. And then instead of just 10 compounding periods, we have 10 times 365. So we have thousands of compounding periods, but we're getting a tiny, tiny, tiny percent of interest. So crunch the numbers. And if you do it carefully, you find that your final dollar amount here is just a little bit more than what you had when they compounded it monthly. So $10,545.68. And you again should find that that's the case. If you're asked any other question where they're comparing compounding, compounding annually to monthly to quarterly or to daily or to weekly or something like that, the more compounding periods you have, if everything else is the same, the more money you'll have. But they're not going to be ridiculously different amounts of money, as you see here. You make about $150 more if it was monthly compared to annually, and then only about $13 more daily compared to monthly.